Hello there, thank you for joining me again today. I just thought we'd examine a topic which a lot of people ask about, which is directional couplers and how to use them and the application. But we're also going to not just look at that, as we've set one up here on the microwave test set. We're going to do some measurements, but that's part of this video. But we're also going to look inside a directional coupler. This particular one that's on the microwave test set right now, this Mecca microwave one, which is just connected up to the scalar probe here, scalar detector on the VNA, and then we've got RF coming in on the left, and then the output's terminated into a 50 ohm load, and then we can measure the performance on the screen, starting at 10 megahertz, and in this case going up to 3 gigahertz. And we'll have a look at that very shortly, but just to show you what's inside these type of, I've stripped down one of these Mecca microwave directional couplers, and that's all that's in them. Nothing fancy, just some strip line where we feed the RF in on one side. This case on the left side here, the RF comes in, and then we've got a strip line which goes to the RF output socket, and of course the unit is built with these little strip lines inside that you can see here, and they're just held in close proximity. And likewise on this section here, we've got again another welded strip line, 50 ohm load on the right, and an SMA connector on the left. And they're very close to one another inside, and that denotes, really, there's two things that denotes the coupling performance. Is the proximity between these two conductors for the incidental, the incident RF, which is at the bottom, coming along this bottom strip line or tune line, and then the top section here, how close they are in between the isolation, and that denotes the level of coupled output on the SMA. But you can get them bi-directional. I mean, the only reason why these are labelled up in out as per this labelling here is so assemblers that assemble them know which way to orientate them, because some depending on what kind of manufacturing task people have got in their particular production line, often assemblers and people who assemble these products may not know which way around to put them in unless they're shown or told. And so likewise, the reason why they mark them up is so that you can see in this particular format, RF coming in from the left couples onto the most left side of this tune strip line, obviously then out to the SMA, and then we've got a 50 ohm match. So any reflected power coming back this way, instead of going on to the coupled line to be fed out as well on the SMA, it's dumped into this 50 ohm load, because RF power coming this way hits the 50 ohm load. So only forward power in this particular arrangement would be allowed to travel from left to right. So transmitter will connect to the left socket, and the 50 ohm load or antenna will connect to the right socket, your dummy load, whatever you terminate it into, or an antenna. And so we're measuring power travelling from left to right, in other words forward power. Now there's nothing to stop you from turning it the other way around, so it measures reflected power. And indeed there are designs that are twin port, where there's a 50 ohm load in the middle, connected, soldered onto the middle of a strip line, and then there's two SMAs, one either side, or two RF sockets, one either side. So it can measure bi-directional power, both forward and reflected, and that's the type of arrangement that you get in RF power meters and things like that. So that's a little rundown of what's inside one. Now, depending on the length of these lines will depend on its operational frequency, as well as the distance between the lines will depend on its isolation at those frequencies. So that's why they alter in size to these directional couplers. They tend to get bigger the lower the frequency they are, because the transmission line's longer, and yet at higher frequencies, like if you watch my other video on the Mecca Omnispectra directional coupler, then when you get to gigahertz frequencies they're quite short, and that's simply because of the wavelength properties that we're dealing with. Again, this is another example. This is an Omnispectra directional coupler. This particular one has got some data on the back, although it's not in very good condition, and it gives you some details as to the type of return loss and forward power reflections characteristics of it. It maps out its isolation between the in and output port and the sniffed output, so it tells you, depending on what frequency you're running it at, from 2.6 GHz to 5.2, it'll give you information there about it. I think that's a 5, can't quite see. I think it is. Yeah, I think it is. Yeah, it's a 5.2 gigs. So the nice thing about this is that it gives you the data for different frequencies, and that's what we'll see when we do this measurement in a moment with this Mecca microwave one, is that it changes its isolation at different frequencies. So although these are designed typically to work between certain frequencies, they're great to have about, because basically you can use these to connect off to different pieces of test equipment, which I'll demonstrate in a moment, at any frequency really. Although this is manufactured, say for example, between 1 to 3 gigahertz, you can use them at other frequencies, both above and below that. Typically more so below, and you can still use them quite safely, and but you just need to know the isolation differences at different frequencies between the input and the output here, because obviously this minus 20 dB specification, which they tend to be around that, most of them anyway, minus 20 dBs at the given frequency, only applies in that frequency range. Whereas if you take them outside that frequency, then they fall off slightly, or they can gain slightly. All depends, which you'll see on the trace I'm going to show you in a moment on the microwave test set. It's on the scale and network analyzer. So that's a little rundown of what's in them, and they're basically how reflectometers and RF power meters are made. This is a version made by Bird, very common RF power meter manufacturer. And this is a reflectometer that's used, or a directional coupler, except we're using a diode rectification, and then we feed the outputs off to a meter, an analog meter that measures power in watts. And again, this is the same principle. We're getting RF power to go one direction, and then we're picking that off, and then we're rectifying it, and then we're passing it to two connections to an analog meter to drive a meter movement. So it's the same design as this, except without just RF coming out there, which is no good to power an analog meter. We need to rectify it with a Schottky diode, smooth it with a capacitor, and then put an RFC in a radio frequency choke to prevent any coupled RF from leaking out of these contacts. And then we feed them then to a analog meter, a meter movement, and that's how we can make a RF power meter. And so naturally that's another method of it. In addition to that, what's great about these is you can use them for measurement capabilities with test equipment, such as the spectrum analyzer that we've got up here. We can connect the spectrum analyzer to this port here. We can stick lots of power in and not worry about damaging the spectrum analyzer. And likewise, when we're one of the other applications is a microwave oscillator such as this, can connect to the directional coupler, and we can couple off a signal then from this without directly influencing the input impedance, because some oscillators like YIG oscillators and VCOs and DROs, electric resonant oscillators, have very high impedances, and in some cases, like a DRO, direct drive before amplification, would have a very high impedance, and so we would need to amplify that signal up to sufficient level that it can provide then what will be a 50 ohm output, or match it to a 50 ohm output, to be then fed into something like this. But if you were to directly connect a capacitor on the output of the oscillator and feed that off then to a detector circuit, be it a crystal detector, power detector, RF power, feed it into a pre-scaler, for example. Most ICs that are on phase lock loop circuits, such as pre-scalers, programmable dividers, they don't work at 50 ohms. They've got higher input impedances and they need to be matched to that. And by introduction of matching networks and couplers and attenuator pads on the output of oscillators to feed back a signal back to a synthesizer, phase lock loop circuitry, means that that can create instability in the oscillator, and it can also load the output at higher or lower impedance than is necessary and cause distortions and reflections and phase noise, things like that. So having a directional coupler doesn't directly influence the output of an oscillator, no matter what it is, whether it's a DRO, a VCO, a YIG oscillator, whatever the oscillator may be, or transmitter. It does not directly couple this output here to the what is the input. It's a sniff, if you like, and therefore this is a popular method for decoupling signals without influencing the input impedance or the output impedance. And so that's one of the reasons why these directional couplers are used quite a lot. Now you can also feed this to a local oscillator on a receiver as part of the receiver circuit as well, so you can actually use a transmitter source to drive a mixer stage in a receiver in order to make a transceiver. You can also feed that off to an ALC circuit if you may want to rectify the output of this, similar to what's going on in here with diodes, to rectify the using fast switching Schottky diodes to rectify the RF into a DC level, so that can be applied then to a an ALC control circuit to control the transmitter's output, depending on what type of VSWR is coming back, if it's obviously in that arrangement. So any reflected power coming back will be coupled on the output of this port, but it'll ignore forward power. So you can do all sorts with them. They're very useful, and indeed this is a typical example of a crystal detector. This is actually a diode rectifier that works up to 12 gigahertz, and that would then connect in line in a very similar fashion, and you'd have a DC output here from the BNC proportional to the RF coming in and out, but again that directly loads in that form there the RF signal that's coming through. So whereas if it was connected, you know, to the SMA, then we would rectify the RF coming off, and it would not influence directly the signal coming through the directional coupler because of the isolation. So there is direct methods of measuring RF signals, and there's indirect, and this is an indirect way of measuring an RF signal. And of course one of the advantages of these is we can use them in all kinds of different measurement applications for measuring VSWR and forward power and what have you. So there's quite a lot that you can do with them, and they all have different power handling capacities as well. Some can only handle milliwatts, some can handle watts, hundreds of watts, kilowatts. I think this particular directional coupler is specified up to 1000 watt, 100 watts forward, and reflected 25 watts I think it is. So yeah, so that's what that can measure. So that's just a little example of that. Now what we've done here, we've set up an experiment where we've got one of these Mecca microwave directional couplers connected here. So we've got the RF in coming in at 0 dBm, which is equivalent to 1 milliwatt. The RF out's terminated into a 50 ohm load, and then we've got the scalar detector on the output. Now it does say on the can there, it says minus 20 dBs. So whatever we're giving in on the input on the left, we should be getting minus 20 dBs lower than that coming out on the SMA. So what we're doing now, we're sweeping, I'll just switch that light off, we're sweeping a very wide frequency range here. We're starting at 10 megahertz on the left, and we're going right up to 3 gigahertz on the right. So its actual specification is minus 20 dBs. Now I think the frequency range for that, when we look it up on Mecca's website, is 800 megahertz to 3 gigahertz. It's been written on the back of this one, but I don't think it is that. But here we've got a frequency with the marker in the bottom middle, which is 912 megahertz, and we've got 19.51 dBs in the top left, in the green, in the very top left, in the red box there. You'll see it says minus 19.5. Now if I move the frequency of the marker and we go up, let's have a look here. Markers, that's it. Right, so if we keep an eye on the bottom middle where it says the marker there, and the frequency currently is 1.0839849 gigahertz. If we have a look at the top left as well as I move that frequency, you'll see that it generally keeps it's around about, I'd say, 1150 megahertz, roughly around about the 20 dB mark. If we move it back the other way, let's have a look. I think it'll more or less keep it for a little bit till we get to round about, again, nearly 20 dBs there. There we are, look, that's 20 dBs, then 21, 23 dB, so round about there, that's about its spec there, which is 718 megs to, I would say, if we get a dB roughly, difference there, around about 874, 19, about a gigahertz roughly, and then it falls off a bit, 18, 17, 16, 15, 14 dBs. It more or less keeps 14 dBs though, right up to, I'd say probably 2.5 gigahertz roughly there, and then it keeps climbing, does the RF level, to minus 12 dB now, right up to 3 gigahertz roughly, minus 13 at 3 gigs. So if we go right down again, obviously we can expand this trace out as well for different frequencies, but even way down here in the VHF UHF spectrum, I mean at 450 megahertz it's minus 24 dBs isolation, and down at VHF here 144, 142 megahertz it's minus 35 dBs, and even right down to VHF low band at 70 megs it's 41 dBs, and then way down here minus 50 at 10 megahertz, 20 megahertz. So you could use this at HF frequencies as well as at VHF, UHF and at microwave frequencies. So it's quite a useful piece of kit to have, you know. I mean, you can do all sorts with this, but the nice thing about it is that you can use it for sniffing RF signals. So, you know, it's not just usable in the design frequency. After all, it is just a strip line, you know, just like any reflectometer or power device, directional coupler. It's the fact that it's usable at all kinds of different frequencies, so that's what makes them quite a nice little device to have. And of course you can make many things out of it as well, you know. So, you know, I mean, for example, you can use it not just for in the case that we just spoken about there, but we can use, if that's the SMA and that's the 50 ohm load, and then we've got the internal strip line, and then we've basically got the RF in and RF out connectors. We can, if we want, feed that signal off directly into a mixer. Then we could put amplifier stages in or whatever prior that, depending on what RF level that we've got, and we've got an RF amp, and then obviously an antenna, and we can use this then to produce an IF, intermediate frequency, for then obviously mixing again if it's a double sub heterodyne receiver, for example, and then we can obviously introduce a local oscillator from a crystal or a VCO, for example, and again the output of that then could be amplified and then discriminated to then obviously produce a received signal. And here of course we would then naturally, to obtain that, we would have an oscillator or a TX. That could be a transmitter, could just be an oscillator, and that itself then could connect via a relay switch, for example, to an antenna. So if I just try and draw that separately, so we could have like a relay, and get rid of that second. That's just a typical example, so we can switch between transmit and receive. So you know, we could use that for that particular circumstance. Another one obviously is using the same arrangement where we've got the directional coupler again, with the termination line internally, and we could use it in this context for measuring RF forward power, but in addition we can sniff off for other applications, so it's used in the same format as it would be for RF forward power. And again we would have an oscillator or a TX exciter that would connect into the input port, and then we would feed this out then through what would be a programmable divider IC, and then that would then go into then what would be then the synth, and then the output then will go into a loop filter. So you know, obviously we would be having a control voltage then coming out of that, and we will then be feeding a control voltage as then a steady state DC or whatever onto this VCO. So that's your loop filter. And so what we're doing then is we're obviously got a reference oscillator which feeds the synthesizer as well, so that's how it knows what its reference is, its reference signal. And so these two are compared. You know, the fundamental signal that's leaving the oscillator or transmitter is sniffed off and sampled back, typically divided by 64 or 65, and the divided frequency that ends up here on this point then is compared against this signal, and when these two signals reach the same frequency, then it's said to be in lock. We get a locked loop, and hence the term phase lock loop. So again, that's another way that a directional coupler can be used in that circumstance as well. So there's all sorts of different applications that you can use them for. That's just a quick basic example. But here we've set up an experiment. We've got a spectrum analyzer on, and then naturally we've got the microwave test set there. So if I set the source up on this to be a carrier wave instead of a swept wave, so we can go to source, we can select source mode, select what is CW, then we can go to source functions, select source mode, set frequency 900 megahertz, and then we can use that now to couple that into what is the output then, the sniffed output from the directional coupler. So here we've got the RF cable from the spectrum analyzer, and we'll just fit that on there, connect it up, and again stiff cable, so we'll connect that up, and then we can then put in a frequency on here, frequency, and then we'll put in 900 megahertz, and amplitude, megahertz, and we're getting a signal pulse there. And we'll set the span to 200 megahertz. So if I put the marker on a second and move the marker, we're getting, when we look at the screen there, minus 20 dB. Can you see it? It's just there. So at 900 megahertz it's giving minus 20 dBs, which is what it's designed to do. But naturally at other frequencies that figure will change, but it doesn't mean you can't use it. It just means that as long as you're aware of what its differences are at different frequencies, hence the reason why, you know, we've got a table on the back of this that's a bit tatty, but at least it gives you an idea of what coupled output level there would be on that kind of a directional couple at different frequencies. And if you've got that data and that information, then you can use it in any example. You know, you can use it in forward power measurements, reflected power measurements, VSWR. You could use it, for example, in producing a local oscillator for a mixer, if you know what level it was going to produce on the output. You could do all kinds of things with it. So these are not to be overlooked, these devices. If you get the opportunity to acquire these, then by all means, you know, you would not be doing yourself out of anything by buying one of these. So that's it from me, and thank you for watching the video, and catch you in the next one when we'll look at some more microwave components. Thank you, bye bye.